So we have discussed how the estimates are obtained. Now we'll see that whether those estimates are unbiased, and also we'll see the variances. It must have a minimum variance. Okay. Now we have seen that beta head OLS, ordinary least square, is equal to x prime x inverse x prime y. So x matrix of the independent variable, transpose it, multiply by x matrix again, and what matrix we will get, invert it. We'll have to find out the cofactor, transpose, then determinant, and we'll have to find out the inverse of that. And to that inverse matrix, multiply by transpose matrix of x and the y matrix. What resultant we will get? We multiply this by the inverse matrix of this. Now here we have seen that beta head OLS is equal to x prime x inverse x prime y. Now if we put the value of y here, so this will become x prime x inverse x prime y, means we have got x beta plus u. So this is equal to beta plus x prime x inverse x prime u. Now when we multiply this, then we'll get x prime x, already we have, and we'll get another x prime x. So x prime x inverse multiplied by x prime x is equal to identity matrix. It is something like numerator divided by the denominator. It is 1 by x and into x prime x. So it becomes identity matrix. So this shows that beta head, that means estimates, is a linear function of the true but unknown beta. It is a linear function of true. So this is the estimated beta and this is the unknown beta. And the disturbance values. So it is the linear function of the unknown beta and the disturbance term. So U1, U2, so on up to U1. In a repeated sampling process, if we repeat this sample, so suppose we do 100 sample, now we'll discard that 100 sample, we'll again collect a new set of 100 sample, then x values will remain fixed. It will give different sets of u's. In that case, the error will be different. It will have a different set of error values and hence a different factor of beta. So as a result, the beta factor will be different. Taking expected values of both sides. So if we take expected values of both sides, then expected beta head, that means estimated beta, is equal to expected beta plus expected this. Now, so beta head plus x prime x inverse, so let us rearrange the term, and x prime expected u. So if we remove the bracket, it will be like this, x prime expected u. Now we know that according to assumption, expected u is equal to 0. So if it is 0, then this whole thing will be 0. So that means beta plus 0. Beta plus 0. This is equal to beta. So expected beta, estimated beta is equal to beta. So we have got earlier that in this order, then these square estimates are unbiased. So if our estimated beta is equal to the unknown beta or ordinary beta after taking a new set of samples, then we say these square estimates are unbiased. Okay. So now coming to the variance, so let us consider expected beta head minus beta into beta head minus beta prime, because transpose of this and this. So this is multiplied by transpose of this, and these are all vectors. So we can express in the matrix that expected beta 1 head minus beta 1 square, rows and columns. So the first row, so this will be the square, and that means beta 1 head minus beta 1 into beta 1 head minus beta 1. So it will be a square. And next will be expected beta 1 head minus beta 1 into beta 2 head minus beta 2. So it is, this is for beta 1, this is for beta 2, beta 3, so on up to beta k. So this way expected beta 1 minus beta 1 head minus beta 1 and multiplied by beta k head minus beta k, it is estimated. Now you see this is square, and this shows the variance, that is the diagonal elements will be variance, and this is the covariance of beta 1 and beta 2. This is the variance of beta 1 and is the variance of covariance of beta 1 and beta 2, the covariance of beta 1 and beta k. So this way for second row we can find out that estimated beta 2 minus beta 2 into, so beta 1 minus beta 1, so it is again the covariance, and next will be expected beta 2 head minus beta 2 square, so this is again the variance of beta 2. So here second row and second column, here it is first row, first column. Okay, so this way expected beta 2 estimated minus beta 2 into beta k estimated minus beta k. So this becomes the covariance. So this way you can expand up to beta k variables and beta k rows. So so it is a symmetric matrix rows. Then last will be beta k estimated minus beta k and beta 1 estimated minus beta 1. So kth row again, this is for second column, beta 2 minus head minus beta 2, and so on up to expected beta k minus beta k square. So the square figure of in the diagonal, it represents the variance, and all diagonal elements, that means towards the right and towards the left, above and below, these diagonal elements are covariances. So it is a symmetric matrix with variance and covariance. Now from above, we discussed earlier that beta head minus beta is equal to x prime x inverse x prime u. So if we put the value of beta, then we will get that x prime x inverse x prime u. And variance of beta head is equal to expected beta head minus beta into beta head minus beta prime. So this is equal to, if we put the values, x prime x inverse x prime u, and for this it is a transpose of that, so it is a u prime x. So we will not write x prime, but as it is a transpose of this, opposite of that. So it is x and x prime x inverse. Now here, if we arrange the term, so we have x prime x inverse and x prime x. That means, again, as we got earlier, so it will be cancelled. It will be cancelled. Okay. So x prime x inverse is a symmetric matrix, as x prime x is a symmetric matrix. Okay. Now variance beta head is equal to x prime x inverse x prime. So let us put expected u prime, then x prime x inverse. Now we know that expected u prime is nothing but sigma square I. That means sigma square into identity matrix, as we say, we got it in the assumptions. So x prime x inverse x prime sigma square into identity matrix and x into x prime x inverse by assumptions. So it will be cancelled and variance will be beta head is equal to sigma square on the x prime x. So one x prime x inverse will be there and others will be cancelled. So variance of beta head is equal to sigma square x prime x inverse. So this means the variance will be in the diagonal elements will be the variance, and off diagonal elements are covariances. So covariances are 0. So covariances are 0 and variances are sigma square I. Now if we take sigma square, that means value here, sigma is a constant variance, and if we take sigma square out, so it will be x prime x inverse. So it becomes an identity matrix. So that means sigma square in. So variance of beta head is equal to sigma square in. That means our assumption is satisfied. Okay. So goodness of fit we have discussed in details in the two variable case, and we have the PDF also. One can go to details of that. Now we'll have to see whether the estimates were we have obtained through that beta head OLS estimates to matrix. Now we'll have to examine whether the model is fitted best, and that we will see through R square values, as we have discussed earlier. It is the coefficient of multiple determination. So the formula is beta head prime x prime y. So we have to multiply. But estimate we get, you transpose it, then multiply with transpose x into y. So all these three will be multiplied. Minus 1 by n, the n is the number of observations, and summation y square. That is the sum of the dependent variable, values of the dependent variable. So y prime y minus 1 prime n, 1 by n into summation y square. So this ratio is the R square values. Now it should be higher than 0.6. Okay, if it is 0.8, 0.9 is very good. But if R square value is very low, then the model has not been fitted well, or the variables we have considered are not explaining the total variation on y properly. So we may like to change some variables, or we will have to set the data and so on. Now adjusted R square. So the R square is often adjusted. So 1 minus S square by SY square is equal to 1 minus summation E square by N minus K. So this is the sum of the square of the error term and divided by number of observations minus number of variable. Okay, so divided by summation Y square into N minus 1. And the relationship between adjusted R square and R square. So relationship is 1 minus N minus 1 by N minus K into 1 minus R square values. Or adjusted R square is equal to 1 minus K divided by N minus K. So number of independent variable, explanatory variable, and this is the number of observation minus number of explanatory variable plus N minus 1 by N minus K into R square values. So when it is very high or very low, then we can adjust it. So thank you very much for watching. Go on watching, we'll continue the other part. So thank you very much, and please share.